We have been talking about ray tracing, right. So, the idea here is that we want to simulate a process which we observe in reality, how the objects or the scenes are illuminated, right. So, typically what is seen is that if you have a light source here and there are objects in the scene and this is your camera, right. So, the way we see is that the interaction of the light source happens through the rays which are coming from the light source, right, and whatever gets intercepted through the camera here is what we observe, right. That is what the process of rendering here is, right. Now, the problem which we observe here is that there are too many rays which are coming out of, let us say, a light source or many light sources, which may or may not contribute to the formation of the image, just because of the fact that many rays may not get intercepted here, right. So, the effort which is being applied here is perhaps too much what we just count for the image, right. So, this is not perhaps an efficient way of generating an image. So, what we do is we reverse the process, right. So, this is called as a forward ray tracing. Then if I reverse the process, then we are talking about backward ray tracing, where we start from the image plane itself, the pixels of the image plane themselves, right. So, there is a ray which is emanated or shot from the eye or the viewer for each pixel in this image plane, right. And then depending on the nature of the object or the material of the surface of the object, there will be a certain behavior to that ray which intersects the object, right. So, it may get reflected, it may get refracted and so on, right. So, the idea here is that we would trace that ray to decide the illumination of the point which is intersected by the ray, right. So, this backward ray tracing is actually nothing but ray tracing, that is what we study, fine. So, if we look at now a simplified situation where we consider that the ray, see there are two issues when we are talking about rendering, right. What are those? One of them is that we should be able to decide what point is visible, right. So, determining the visibility of the scene, that is one issue, that we can ascertain by considering the closest point with respect to the viewer, right, which is given as a consequence of looking at the intersections with the scene of the ray, right, and then you consider the nearest point which is intersected. That is how we establish the visibility in the scene, right. That is one issue which we resolve through ray tracing. The other issue is to determine the illumination at the point of intersection which we have ascertained to be visible, right. So, there we just apply the illumination model which we have studied, right. Now, as I said in the previous picture, that depending on the material of the object, the ray which comes to an object may get reflected or may get refracted, right. If I discard those so called secondary rays, right, these are the secondary rays, then we are talking about only one level of tracing of the rays, which is the ray which gets off the viewer to the object or the scene, and wherever it intersects, the first point of intersection with respect to the viewer is the point to be rendered, right. So, that is a simplified scenario where we discard the further secondary rays beyond the point of intersection, right. So, that we call it as a ray casting or one level ray tracing, right. So, when we do this, the issue comes are finding the ray object intersection, that is the one task, and the other thing is apply the illumination model, right. Applying illumination model we have already studied. So, let us try to see the ray object intersection. There also we looked at last time the ray sphere intersection, right. So, just let me review certain aspects of it. So, this is what I said, these are the two issues, the visibility test and the illumination model, right. These are the two issues related to ray tracing. Okay. So, when we look at ray object intersection with the sphere as an object, we consider a parametric form of the ray, right. The ray is defined as the origin of the ray, which is a point r 0, and the direction of the ray, which is defined as r d, and the parameter t. Right. This is a line definition. So, clearly we use t greater than 0 because we are considering that we will look at the rays which emanate from the origin of the ray, which is the viewer or the eye, towards the scene, right. So, we are not concerned about the rays which are in the opposite direction. Therefore, only positive t's have to be considered, right. So, for the purpose of simplicity, we may consider the direction of the ray to be normalized. So, we have a unit vector, right. So, this is how we look at the definition of the ray, which is in parametric form. So, as far as the definition of the sphere is concerned, we considered this as an implicit form, where we define the sphere through the center and the radius of the sphere, right. So, we have an implicit equation for the sphere, which is x s minus x c square plus y s minus y c square plus z s minus z c square equals to s r square, right. So, x s, y s, z s is any surface point on the sphere, right. So, now obtaining the intersection of the ray with sphere turns out to be substituting the equation of the ray into this equation and solve for t, right. That is what it becomes. So, this actually gives you a quadratic equation in t, right. So, is in the form of a t square plus b t plus c equals to 0, if you substitute the ray equation into the sphere's equation, where these are the coefficients a, b, c, right, in the known quantities, in the quantities you know, right. So, the solution of this could be found out, right, and we would consider, so there will be two values to t, right. So, we will consider the smallest value of t because we are looking at the closest point, right. Now, given the point of intersection here, let us say x I, y I, z I, the other problem comes is to find out the normal at that point, right. So, in the case of sphere, it is a very simple situation, just the radial direction from the point gives you the normal, right. So, this is the normal, which is x I minus x c, x c, y c, z c are the coordinates of the center, right, and S r is the radius. So, this is a unit normal vector at the point of intersection which you have computed. Right. Calculation of normal is essential because we would like to compute the illumination at that point, which comes from the normal, right. Okay. So, this was a very simple way of obtaining intersection of ray to sphere, right. There is also another way to look at it, an alternative way to find out the intersection with the sphere, which is somewhat a geometric approach, right. So, consider this as a sphere with a center here O. This is your origin of the ray r 0, right. This is some vector, let us say L, and this is the direction of the ray r d, which goes from here. So, in effect I am trying to find out these points, right, these green points, and I will select this being the closest. Right. Now, geometrically I also have, so if I if I form this line there through r naught in the direction of r d, this particular length is nothing but the radius of the sphere, right. Let us say this distance is the distance d from the origin of the sphere to the ray direction, right. And let us say this particular distance which is traversed along the ray direction is T C A, right, and this distance is T H C. Fine. So, if I can somehow relate this distance in terms of T C A and T H C, I should be able to get the T's which would give me the point of intersection, right. So, now the question is whether I can compute these T C A and T H C, right. So, what are we saying? This L is nothing but O minus R 0, fine. Now, what is T C A? This is nothing but a projection of L to this direction of the ray, right, which is nothing but dot product, right, which is also L transpose times R d, right. So, I can compute T C A, I can compute L, I can compute T C A, fine. Now, there are also cases where I can do some elimination of further computation, right. So, if I know that T C A is less than 0, that is nothing but saying that T's are positive, right, then there is no intersection, right. It is on the other side of the ray, fine. So, I can compute T C A, right. Now, let us look at the other thing. Now, how about D? D is nothing but this L square minus T C A square, right. T C A I have already computed, L is L T L, right. So, I can compute D, fine. Now, again if D is greater than R, there is no intersection, right. If D is greater than R, then there is no intersection, fine. Okay. So, the next thing is to get the THC. So, THC is nothing but r square minus d square from this triangle, right, square root of r square minus d square. So, then T of interest is TCA minus THC and TCA plus THC, right. These are the two T's, T naught and T 1, and then you take the smaller t, right. So, you can also do the same computation which we did algebraically by substituting the Ray's equation into the sphere's equation and solving for t. You can also do that in geometric form, right, using geometry. Fine. Okay. So, this is the sphere ray intersection, right. In a similar fashion, we can now look at other kind of objects, right. So, let us say if I look at ray plane intersection. So, once again I consider ray to be defined in a parametric form, right, exactly the same way as I consider for sphere, right. And this plane is again defined in implicit form a x plus b y plus c z plus d equals to 0, right. And I can assert that a b c gives me the unit vector. So, a square plus b square plus c equals c square is equal to 1, right, which in turn also defines the normal of the plane, right. So, I do not have to compute explicitly normal of the plane, I know from the equation of the plane itself, right, and d is nothing but the distance from the origin, right. So, this is the equation of the plane I have. So, exactly the same way as I did in the case of sphere, I can substitute this Ray equation into this and solve for t, right. Okay. So, this is what is done here, you substitute Ray equation in plane's equation, right, and solve for t. So, when we look at the solution, we get in the numerator a x naught plus b y naught plus c z naught plus d, right, and in the numerator we have a x d plus b y d plus c d, right. So, further simplification can be observed by looking at this as nothing but in the dot product form of vectors, right. So, this is nothing but dot product of the normal with r 0 and this is nothing but dot product of normal with ray direction, right. Now, before you explicitly compute t, you probably need some word of caution. You do not want this to go to 0, right. So, if this is 0, what does it indicate? Ray is parallel to the plane, right, and therefore, there is no intersection. Okay, so, that is what is done. So, if I just look at the denominator part of it defined as V d, which is the dot product of the normal and the ray direction, then if I check for whether it is 0 or not, then only I proceed for the intersection, right. So, if it is 0, there is no intersection. If it is, there is another condition which is also useful, that this is the ray direction, let us say, this is the plane which I am considering and this is the normal to the plane, right. Now, this V d, which is nothing but the dot product of the normal with the ray direction, if it turns out to be greater than 0, what does it indicate? It basically indicates that, see, in that case this normal would have been in this direction, right. So, the plane is facing in the opposite direction of the ray, right. So, with respect to the visibility, if the ray is considered as the ray coming from the viewer, right, if there is a normal which is pointing away from that, you will declare that that is not visible, right. But if, let us say, for the reason that you just have to assign certain attributes of color or illumination, right, let us say it is a light ray or some other ray which we are using for painting the plane, right. So, if this is a situation, then I am talking about the other side of the plane, right. So, I am basically, I can consider plane to be two sided entity, right. There could be front side and back side, which may have its own illumination, right. So, then I can use the flipped version of the normal to compute the illumination at that point, right, for the purpose of computing illumination at that point, right. But here if we are looking at this, that there are only one sided planes, right. So, we are not interested in rendering the back side of the plane, then we just eliminate that, right. Okay. So, this is how we compute the intersection. So, the as far as the numerator part is concerned, that is what we had in the numerator, right, which I can call it as V 0, right. So, this just as a t is equal to V 0 divided by V d, right. And again, if t turns out to be less than 0, then plane is behind ray's origin, therefore, do not compute intersection, right. Well, this will be elaborated further, because we have already computed t, which in turn gives you an intersection point, right. But there could be further utility of this. And if we find that t is in the valid range, right, then we substitute that t to get the point of intersection, which is x i, y I, z I, which is this, fine, and the normal is nothing but the p n itself. Right. Now, the problem is that once we have figured out the intersection with respect to a plane defined in its implicit form, a x plus b y plus c z plus d equals to 0. See, typically you would have an object defined as a plane which has boundaries, right. This is sort of an infinite plane, right. So, your object would have certain extents, or you may have an object which is composed of several polygons, right, collection of polygons, right. So, this is, then this becomes only part of the intersection computation, right. So, you need to establish whether the point which you have obtained here through this intersection is within the extents which you have defined for the plane, right. So, that is what we call it as the containment test of the point, right, whether that point is contained within the extents of the polygon, right. How do we check that? Yeah, see, the polygon is actually defined through the boundary points of the polygon, right? And now you have also found out the point of intersection with that plane, right? So this Ri is known to you. The question which is being asked is to answer whether this Ri lies within that boundary points or not.
So simple point clipping.
Pardon me?
So simple point clipping. We
Simple point clipping.
I mean, we consider the
point.
Right. So that is one way to look at it. Another way to look at is something that also you have seen.
Parameter is greater than 1 if we represent it in a form of parameter.
Parameter of the boundary.
Yeah.
Okay. Yes, that's also possible. So let me give you the ways you would like to see here. So one possibility is something which you have also seen as scan conversion. Right. So what are we saying here is that if I find out a point P here, right, let's say this is the point P, right, and if I shoot a ray in some direction, then the number of intersection with the boundaries of the polygon can indicate whether the point is inside or outside. Same as this parity check, right? Fine. Again, there could be special cases
Like
where the point is at this. Right?
so in that case, we'll consider double intersection.
Right. So one way to do is consider a ray coming from that point, right, in some direction, and find out the intersection with the edges of the polygon, right, and the number of intersection is an indicative to whether the point is inside or out. Right. So if the number is odd, the point is inside; the number is even, the point is outside. That's the idea. Fine. There is another way to look at it, which is very commonly used, particularly when you have the polygon to be a triangle. Okay, that's where one can look at the parametric definition of the point with respect to the boundary points. Yes.
So in this case, if we are choosing the direction of the ray we are emanating from this point at random, then for some particular case the ray will coincide with one of the edges.
Yeah. So see, typically what is done is that you take the projection of this polygon, right, perpendicular to the normal of the plane, right. There, when you consider the point, and then you can fix the axis or a direction. So you can also compute some sort of a principal direction of the polygon, and then start shooting in that direction. Or you can align your polygon in some coordinate axis and then shoot the ray in that direction. Right. Okay, so now let's see if we consider the polygons to be triangle. Right. So we have a better way to see this process of containment. So the question which we are asking here is, first of all, so given this triangle V1, V2, V3 as its vertices, there is a point P here inside this triangle, right. So we would like to represent this point P in terms of these vertices, the vertices of the triangle. Okay. And the way it is done is we use what are called as the barycentric coordinates. So, barycentric coordinates actually gives you a desirable combination of the parameter u, v, w or the weights, which you can use it for the various vertices, right. Now, how do we compute these barycentric coordinates? So, let me elaborate on this. See, this is something similar to if you had, let us say, a line AB, right. Now, for a point within this line, right, if I have the parameter t, right, then I can always define this point P as 1 minus t times a plus t times b, right. So, this 1 minus t and t are nothing but the barycentric coordinates, because what are we doing? We are basically defining a point on the line as combination of the two endpoints using a parameter, right. Or I can write, let us say, u a plus v b, where u plus b equals to 1, right. So, this u and v are nothing but the barycentric combination or barycentric coordinates for that point. Okay. So, similarly, we are trying to compute these u, v, w now, because we have 3 points in the boundary, right, which are the barycentric coordinates. Okay. So, here we had used the distance. So, t is nothing but a distance measure from the two endpoints, ratios of distance, that is what it is, right. So, in the case of triangle, what can we do? Any distance from actually we use the areas. Okay. So, what we define is, they are also called the area coordinates. So, let us say if I define this area in front of the vertex V1 as A1, similarly A2 as this area and A3 as this area, right, and let us say the total area is A of the whole triangle. Then these barycentric coordinates or the area coordinates are nothing but the ratios of these individual areas to the total area.
A1 is opposite to V1.
A1 is opposite to V1, right. So, you can also define, let us say, E1, the edges also, right. Either you can take the vertices or the edges. So, if I am defining V1 as this, then E1 is defined as this edge, right. So, we define these u, v, w as nothing but the area coordinates, right, which means now this u is nothing but A1 divided by A, v is nothing but A2 divided by A, and w is nothing but A3 divided by A, right. And we also observe that u plus v plus w equals to 1, right, and all these coordinates are greater than or equal to 1. Right. So, they are convex combinations, right. So, how does it help in containment test?
So if there exists such
If there exists UVW, right. So, what do we have to do? We basically have to compute the UVW, right, from the point and figure out whether these conditions are satisfied. Right. If these two conditions are satisfied, then the point is inside, right, otherwise the point is outside. So, where else can we use these barycentric coordinates, which we have already studied in earlier?
Use it in any convex polygon. Because we are finding out
No, my basic question is that since, see, what is this basically doing? Is basically doing some sort of an interpolation with respect to the vertices of the triangle, right? That's what it is doing. Now, we have looked at the shading models, right? Polygon shading, Groth shading, Ponk shading, right? What do we do there? We basically do this, right? We do an interpolation of the point to find out the intensity or the normal, right? So, the only difference is there it was considered for a general convex polygon. Here I am considering the triangle. So, in fact, if you use this triangle as the polygon, some of the limitations or the artifacts which could be produced there can be eliminated, right, because you are always finding the combination with respect to the vertices of the triangle. Right. So, remember we were talking about rotation of the polygon. If it is done, then the edges become different, therefore, the point gets different coordinates or different intensities, right. So, if I do the combination with respect to the vertices of the triangle, that will never happen. Right. So, anyway, so you can use this at various applications, right, various applications. Okay. So, this takes care of basically ray plane intersection.
Sir, can this be extended to, like, I actually mentioned it, but I don't think so it can be extended to any n-sided polygon.
It cannot be, because these are also unique. They could be a different representation, not necessarily the area coordinates. So, his question was whether this can be extended to an n-sided polygon.
Yes, sir, but like any point can be represented as a convex combination of.
Yeah, that is true. That is true. But what is that convex combination? That is a different question. Right? So, that's you are not trying to answer it. Okay, so that is not this combination. The uniqueness is not preserved. Okay. Now, in fact, this can be extended in 3D though. 3D means if I am having a volumetric element. See, we started with a line where we looked at the barycentric combination to get a point on the line, right. Similarly, here a point inside the triangle is a barycentric combination of the points at the vertices, right. Now, if I take a volumetric element, tetrahedron for instance, right, then again the containment test within that tetrahedron can be established using barycentric coordinates, where the barycentric coordinates will be computed using the volumes ratio. So, there you will use the volume ratios just exactly the same way as the area ratios here. So, here you will have for instance V1, the volume of the tetrahedron which will get formed by the point inside the tetrahedron divided by the total volume. Right. Okay, so next we move on to ray quadric intersections. So, quadrics are shapes which you are familiar: cylinders, cones, sphere is also a quadric, ellipsoid, paraboloids, hyperboloids, etc. Right. So, again the idea is very similar to what we have done in the case of sphere or plane, right. So, you have the implicit form of a quadric like f x y z equals to 0, right, which is given here: a x square plus 2 b x y plus 2 c x z plus 2 d x plus e y square plus 2 f y z. This is 2 g y h z square plus 2 y z plus j equals to 0, right. So, again if I consider parametric form of the ray, then it is just a matter of substituting this ray equation into this and solve for t, right, just exactly the same way as we did it for sphere, right. So, in fact, there is an interesting way of representing the same quadric is something like a matrix form, where if I have this is in the homogeneous form x y z 1, right, then this is the coefficients are represented by a 4 by 4 matrix, which is a symmetric matrix, right. So, A B C D here in the column, right. So, this part of the matrix is same as this part of the matrix, right, and again you have the column of the point x y z equals to 0, right. So, this is also same quadric which we looked at. Fine. Now, the next thing comes. So, we can solve again as a quadratic equation in T, right, and if we have the condition that AQ is not equal to 0, we have the two values of T given here, right, with the change sign of this minus here plus here, right, and if Q happens to be 0, then we have the simpler solution T is equal to minus CQ by BQ. Right. Okay. So, once we have again found out the point of intersection, the next thing comes as what is the normal, right. What is the normal at the point of intersection? How do we find out the normal? So, clearly it is not as simple as it was in the sphere. So, what do we have? We have the implicit form f x y z equals to 0, right. So, how do we find out a normal for f x y z? Del. So, we take the del function, right. So, that is what it is. So, the normal is nothing but taking the del function for f, which is del f over del x I, del f over del y I, del f over del z I, right. Which turns out to be this. Right. So, now the illumination computation can be done. Fine. Okay. So, the next object which you would like to consider is a box. Right. A box is, of course, can be thought as collection of polygons, right, and then you basically perform an intersection with individual polygons of the box, right, and then see what are the points of intersection, right. But another way, excuse me,
we have a ray,
right,
then it will intersect only the front face of only one polygon.
yeah. So, I was just trying to give you a scenario where you could ignore the properties of the box as such and just think this as collection of polygons, right, and then find out the intersection with each polygon, right, and wherever it intersects, the polygon with which it intersects, then again you do some sort of a sort on those to figure out what is the point of intersection, right. But an alternate way is, and which we have already seen in the context of clipping, right. In 3D clipping, it is nothing but finding out intersection of the line which is to be clipped against the box which is the clipping window, right. So, it is just a matter of applying your Cyrus-Beck or Liang-Barsky clipping algorithm. Of course, that requires you to have this box to be a convex polyhedral, right. So, typically when we are looking at box, they are basically rectilinear boxes, right, parallel pipe structures, for which applying this 3D clipping is fairly easy, right. So, just again to recapitulate your clipping, it's a, let us say if I have x in this direction and y in this direction, right, then the same treatment can be done if I add z to it. Then I am talking about the potential points of intersection or the t's corresponding to the potential points of intersection with this ray, right. This is the ray I have as this point. So, this point is nothing but some sort of a near t point or t near point, right, t corresponding to the near point, and this is t corresponding to the far point, which were also thought as the entering points and the leaving points when we were doing clipping. So, this is the same thing. So, similarly, I would have this point and this point as the near and the far point, or entering or the leaving point, right. So, again I can figure out the segment which would be inside that volume by clamping the T min and T max, right. So, all we have to do is we basically have to just apply our 3D clipping algorithm, where ray is nothing but a line through the window of this box, right. So, let us stop here. Next time we will talk about setting up your ray tracing with the similar interface of the viewing transformations which you have done, right. So, where the user would like to specify the eye in some coordinate system, and then you have to get the ray from that coordinate system to find out the intersection in the world coordinate system, right. So, how do you set up that interface, right? That will basically make you ready for the next assignment. Right? Okay, thank you.